From this lecture onward, we will start the study of fault analysis of a power system. That is, we will study various scenarios whenever there is some fault in the power system, and we will try to find the state of the system during that fault. Now, in this lecture, we will first try to see the basics of network theory, which will be required for that. As you have seen in my previous lectures, around lecture number 48 or 52, wherein I have covered the equivalent circuit or equivalent network of a synchronous machine, in which I have shown that a synchronous machine can be shown in steady state as an equivalent voltage source, alternate voltage source, and a reactance which is usually written as XS, the synchronous reactance of the machine. This usually depends upon the field current, and this is usually written as the sum of two reactances. First is the leakage reactance and other is the armature reactance. Okay. Now, the voltage coming at the terminals is usually called the terminal voltage of the machine. Now, for a normal power system, what we usually do, we show that some generator is connected, usually which is a synchronous machine only, synchronous generator. This machine is connected to the load through a transmission line which is having some impedance, Z transmission line, and here it is connected to some load. This is the load, which is again some impedance only, ZL. Now, let us say that there is a fault either at the load end. Fault means that there is some short circuit from the phase to the neutral or the reference. There will be various kinds of fault which we will study further in our course of study. We are assuming that there is a three-phase symmetrical fault on the generator. That means on per phase basis, the line is short circuited to the reference or the ground or the neutral. Now, this fault can be either on the transmission line. Similarly, the worst case scenario will be, that is the maximum fault current will be when this fault occurs at the terminals of the generator. There can be similar cases. So, to study this thing, what we should know? We should know that this system, if we want to try to solve through a network theory, what it is? It is simply equivalent to an AC voltage source, EZ, connected through some impedance Okay, so whenever a fault occurs, what happens? Let us say this switch, closing of switch is showing the instant of fault. So what does it show? That whenever this switch is closed, and let us say if the machine was not on load, that is it was unloaded, this thing was open, then whenever there is fault on the terminals, what happens? It is equivalent to closing of this switch only. Okay. So if I know the response of this circuit, then I will be able to at least predict the response of this circuit. So before going on to this circuit, what I will do, I will try to learn the basics of analysis of an AC source connected through any impedance Z. Okay. Now you know that The network which is shown here is simply an AC voltage source connected through an impedance, and initially it was open. So initially the current IL, let us say this current is IL at 0 minus was 0, and since it is an inductive circuit, IL 0 plus will also be 0, because the current, the inductor will try to oppose the current through it, the change in current through it. So the IL 0 minus is equal to IL 0 plus is equal to 0. That is, the current at instant 0 is 0. Okay. Now we know from our network theory, which we will study, or which we have already studied, if we have already studied the network theory part, that this current IL can be broken into two parts. First one is the natural response, and the other one is the forced response. That is, this response, the current part, the current of this network can be broken into two parts. First one is the natural response, and this is usually, in the form of a decaying exponential. This we will study when we will study the network theory, in which we will see that the natural response of an inductive circuit is of the decaying exponential form. And this is of the form of the forcing function only. Okay, so this will be some kind of sinusoid. Let us say it is some sinusoid based on this thing. Now we want to determine the exact response for this system. Mathematically, we might have studied the solution of differential equations, in which we might have studied particular integral as well as the complementary function, and these two are just the other nomenclature of these two kinds of responses. Okay, so what do we do? First, we know that the natural response is of the form of exponential decay, where this is the time constant, and time constant for an RL circuit is nothing but L by R. Okay, that is the equivalent inductance and the equivalent resistance of the circuit. And the force response, let us say this EG is written as EG max sine omega t plus alpha. Okay, this alpha will help us in mathematically taking the value of this voltage source at any instant. Let us say I want to find that at t is equal to 0, Eg is having some value. So from this equation, Eg will come out to be Eg is equal to Eg max sine alpha at t is equal to 0. This alpha is trying to show what is the value of the voltage source at t is equal to 0. So by controlling this alpha, mathematically I can find the values of this voltage source at t is equal to 0. So this is the significance of this alpha. Okay, now we also know that the power factor theta is usually written as like this, where these are the equivalent inductance and the equivalent resistance. So the power factor angle is usually known to be, for an RL circuit, to be tangent inverse omega L by R, where omega is the frequency, radial frequency of the source. So this forcing function or the force response will be of the form Eg max divided by the impedance of the circuit, magnitude, sine omega t plus alpha minus theta. This we have derived, this kind of force response we have derived in our first lecture of this course when we studied the basic part of the phasor analysis. In that, although I have not clearly told that this is the only steady state response or the force response, but it was already pertinent or already understood that we were dealing with the force response. Okay. Now, as I already told that the circuit was open initially, so the current cannot change instantly. So I know that IT is equal to 0 at t is equal to 0. So I force response and the natural response should be adding to 0. Okay. So I know that A e raised to power minus t by tau plus Eg max over G sine omega t plus alpha minus theta should give me equal to 0 at t is equal to 0. That is, this omega t is 0 at t is equal to 0. So this sum should be equal to 0 at t is equal to 0. So it means A is equal A e minus t by tau, and at t is equal to 0, this is again 1. This exponential is 1 only at t is equal to 0. So it implies A is equal to minus Eg max over the magnitude of the impedance sine alpha minus theta. Okay. So in the next slide, I will write the complete solution of the current of the circuit. Now let us write the complete solution of the current for the current of the circuit. So IL T will be simply minus Eg max over Z magnitude E minus t by tau. This is the natural response of the system, plus Eg max over G sine of omega t plus alpha minus theta. I have also written, I have to write one more term here, sine of alpha minus theta. Okay, so this is the final form of the current which will be flowing through this network. Okay, you can verify this thing that at t is equal to infinity, only the steady state response will be there. So we can see from here that this term will tend to 0 because exponential will decay completely there. So only the force response will be there, which is the steady state response of the system. Again, we also know that this part, the natural response, is having a maximum value minus of Eg max over G sine alpha minus theta. Okay, this is the maximum value of this natural response. So this will be of the form like this. If I take this minus sign inside, I can write it like Eg max over Z sine theta minus alpha. Now you see the importance of alpha and theta. When alpha minus theta is equal to pi, 0 or any multiple of pi, I can see that this term will be 0. So whenever alpha minus theta is equal to 0, then there will be no decaying exponential term in this circuit. So in that way, we can see that only the force response will be present, or the steady state response will be present in the response of the current of the circuit. Now, when alpha minus theta is equal to pi by 2, then I can see that In max will be at its maximum value, which is equal to minus Eg max over Z. When it is equal to 3 pi by 2, then it will be equal to Eg max over Z when alpha minus theta is equal to 3 pi by 2. That is the old multiples of pi by 2. So you see that this alpha and the power factor angle of the circuit controls whether there will be a DC decaying part in the response or not. And this DC decaying part can have a maximum value plus minus Eg max over Z. That is equal to the maximum value of the force response. Now you have seen that we have tried to show the similarity between a synchronous generator and the circuit. We have also found the response of the current whenever this circuit is shown, that is, this is equivalent to a generator being short circuited at its terminal. But there are various dissimilarities also. That is, this circuit will not behave entirely like this response. So what are those dissimilarities? Although this circuit is similar, but there will be many dissimilarities whenever there will be a fault on the synchronous generator terminal, or let us say at some far end, again there will be a different response. That dissimilarity we will see in our upcoming lectures. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.